Hello class, welcome to the STAT 511 week 14 video where we will finish up our discussion on inferences for two or more population means. The objectives for this lecture will be to cover the assumptions needed for ANOVA, pre-planned comparisons, post hoc comparisons, the random effects model, and then we're going to take a look at a practice example that puts everything together. So quick review for the process we use when solving an ANOVA problem. The first thing is when we have our data is to check the assumptions to make sure that ANOVA is appropriate in this scenario. Second, we need to construct our ANOVA model. Third, we will conduct an overall F-test using our ANOVA table. And then steps 4 and 5 will complete any pre-planned comparisons we have, and in lack of that, we'll take a look at post hoc comparisons. So to begin, let's take a look at the assumptions needed for ANOVA. So there are three assumptions for ANOVA. The first is independence. That is, the observed responses, Yij, were collected independently, meaning we have T independent random samples. The second assumption is normality, that the responses for each population are normally distributed. And three, we need to have constant variance, meaning that the population variances are the same, and we may recall talking about homosyntesticity in previous lectures. And so taking a little bit closer look at our assumptions. So each of our model assumptions involves the linear model error terms, epsilon ij, which is equal to each actual observed observation minus the row means, which are a simple numerical approximation of our error term and will be used to develop graphical and numerical checks in assumptions 2 and 3. The assumption of independence can be determined based on the collection methods used in the problem, and usually this is an assumption that's given to us, or we just generally understand that items are collected independently. So as we've checked off our understanding of our first assumption, let's take a look at the second one, which is that non-normality assumption. There are two ways we can really check non-normality. One is to look at a histogram of the NT residuals, EIJ, is sufficient to detect our major non-normality. Ideally, the histogram should be unimodal and symmetric, and we can also use the QQ plot, which we have talked about in previous lectures. I do want to caution you guys on being too harsh, I should say, with the non-normality assumption when we're looking at these um, graphs and plots. If we are dealing with a small sample size, it is going to be a bit harder to assess a histogram or a QQ plot, which is why you may hear me use the phrase, well, it's normal enough given the small sample size. Our third assumption is our equal variance assumption, and there are a couple ways we can check the equal variance assumption. One way is the visual method, which is to look at either a residual plot, side-by-side box plots, or dot plots. With the side-by-side box plots or the dot plots, you should see each category or each treatment or each factor should have approximately equal variance. For the residual plot, you should be looking for a cloud-like shape with no major direction. In addition to our graphical checks, numerical hypothesis tests can be used to check our assumptions. One of these tests is Levene's test, which replaces the responses Yij with the absolute value of our residuals, and then conducts our overall ANOVA F test. In this test, the null hypothesis is that each of the variances are equivalent to the alternative hypothesis, where at least one of the variances is different from the other. So in this case, it's actually better to have a large p-value or an insignificant result. And so the next question that comes up is what should you do when your violations or your assumptions are violated? Well, first thing to do is to closely re-examine your data and data collection procedures to make sure that the data have been correctly measured and recorded. Um, I think I've used this example before, but in my line of work, sometimes people record odd values when something is unknown or missing. So, for example, sometimes people record blood pressure as 0 or 999, which, if your blood sugar or blood pressure level is 0, you're dead. So, you sometimes have to go back and make sure you've caught how they're coding different numbers. Sometimes you need to re-examine the model. There are defects in the model that may appear as violations of assumptions. 3, we might need to consider a data transformation, which we'll talk about in the next slide, or you may need to perform a different test, such as the non-parametric test. As I said in not the last slide, but the slide before that, about looking at the histogram and saying, oh, well, it's normal enough. Well, sometimes when we are working with sample size of, say, 5, we can't really make a determination if that population comes from the normal distribution. So we have to go about taking or using tests that aren't based on some underlying probability model. That is beyond the scope of this course, but it does happen. I've certainly used non-parametric tests in my own work, particularly when I'm dealing with live subjects. So transformations, as I mentioned, um, sometimes we do these variance stabilizing transformations, and often it's when the assumption of equal variance is violated. And sometimes the reasoning is that there's kind of a, quote, issue with the variables themselves, unquote. And what we mean by that is sometimes when we're studying large animals and small animals, there's a great variability in size. And the same thing with plants. So, all plants kind of start out as this very small seed, but large plants grow much higher than smaller plants, and so it can kind of mess with our variabilities and mess with the equal variance assumption. And so we have to be aware of that, think logically, and so we may have to do a transformation of our response, either take the square root or a logarithm, and then perform our analysis on this transformed response. And a lot of times when we do these transformation of our responses, it even helps with our non-normality assumption if we were to reassess our graphs. This is not something we really want to do unless we absolutely have to, because it does affect how we interpret our results, because it's no longer, x correlates to y, it's x correlates to the log of y or the square root of y. And so if we don't need to do this, we don't want to, but sometimes it becomes necessary. And so that brings us to the end of our discussion for assumptions. Again, we have 3 assumptions: independence, constant variance, and normality of the residuals. They're pretty easy to check, and so whenever you can, you should, of course, always do so. As far as for your exam, I'm not going to ask you to create any of those graphs in the scope of checking your assumptions for ANOVA, but I might provide them and ask you to make an assessment. So I may provide you with a QQ plot or a histogram or a Levene's test, and you need to make the assumption or make the assessment whether the assumption holds. Okay, so this brings us to our second objective, which is to talk about our pre-planned comparisons. This is a topic in statistics, particularly when we're talking about analysis of variance, that is very important. As we've talked about in our previous class, our fixed effects ANOVA model has the hypothesis where the null hypothesis is tau I equal to 0 for all I, versus our alternative hypothesis where tau I is not equal to 0 for some I. And our issue with this is that our statistically significant f-test for ANOVA only indicates that at least one of our population means is not equal to the others. It doesn't tell us which population mean, it just tells that there is a difference somewhere. And that's excellent to know that a difference exists in somewhere one of our treatments is somewhat different. But the next question that comes about is, okay, but where's the difference? Or more formally, we are often interested in more specific questions, meaning, is there any difference between the population means? Rather, we're more interested in, is the mean response for some specific level superior to the others, or is there some sort of natural grouping of factor level responses? And you'll see in these examples, some of them have some pretty obvious natural grouping that we use. And so to answer these more specific questions, we can often answer them by posing rather specific hypotheses, which we do have to call multiple comparisons. And we did establish that multiple comparisons, while not great, but they are actually sometimes necessary, because asking the simple question, is there a difference, doesn't get us close enough to the results we're looking for. And so there are two types of multiple comparisons we are really interested in. One are pre-planned comparisons, which we generate prior to our experiment being conducted. And then two, we have our post hoc comparisons, and they're formed as a result of our data analysis. Ideally, we perform pre-planned comparisons, but post hoc comparisons are performed when we have no other choice. So when completing our pre-planned comparisons, we set them up with contrast. And so the most specific comparisons are based on linear combinations of the population means, mu I, and we call these contrast. And so to understand how we set up contrast, let's consider the mice in the maze example. So if we recall, there are 3 sets of 5 mice that are randomly selected to be placed in a standardized maze with different colored doors. And in our table, we see the response time required to complete the maze per each colored door. And so for our contrast, we might suppose that we learn that doors are typically colored black in the mice mazes. So one logical thing the experimenter might want to question is if changing the door color to say red or green will allow the mice to complete the maze faster. So we may be interested in comparing the black door versus the red and green door. And then we may be interested in testing whether on average the black doors provide statistically slower completion times than the mean completion times of the red and green doors. We may want to just compare the red and green doors. There's a lot of different options that we may be interested in comparing. But for now, we're going to operate under this assumption that the standard is that doors are painted black, and we want to see if there is a difference when we have painted it red and green. So for us, this would allow us to set up a hypothesis where we compare the black door versus the red and green door. And so our null hypothesis would assume they are the same, and seeing as we want to assess if changing the door color results in faster times, we'll say black time average is going to be greater than the red and green. And using algebra, we could also rewrite this to being 2 parts black to 1 part red and green. You will notice that I have these interesting coefficients. And the reason for that is we are looking at 2 averages versus 1 average. And so to kind of keep our design balanced, we have to weight them equally, which gives us lead to our definition of contrast. So a contrast is a linear function of whose means coefficients sum to 0. So that is a linear function of our population means. The summation of I equals 1 to t of ai times ui is a contrast if the summation of I equals 1 to t of ai equals 0. And so what we want is we want these coefficients to equal 0 in order for it to be called a contrast. And like I said, this keeps things balanced. So if we consider the linear function for our means mouse example, I said we had 2 parts black to 1 part red, 1 part green. So if we look at our coefficients, that is 2 minus 1, which gives us 0. So therefore we say this satisfies the criterion for being contrast. If we were to leave each of these coefficients as 1, 1 minus 1 minus 1 would equal -1, which does not equal 0, so therefore it would not be considered a contrast. And so as we have talked about doing inferences, to do an inference for a contrast, our hypothesis test would be to test the null hypothesis that the summation of I equals 1 to t of ai mu I equals 0 against any alternative. And our test statistic would be t equal to the summation of I equals 1 to t of ai times our row mean minus 0 all over the square root of MSW over n multiplied by the summation of I equals 1 to t of ai squared, which is compared to the t distribution with degrees of freedom equal to t times n minus 1. And you may notice that this is actually just a generalized version of our pooled two-sample t-test. And we also can construct a confidence interval. And so to estimate the 100 times 1 minus alpha % confidence interval, we use the following formula, which would be the summation of I equals 1 to t of ai times the row means plus or minus t alpha over 2 multiplied by the square root of MSW over n multiplied by the summation of I equals 1 to t of ai squared. And of course, our t alpha over 2 value has our degrees of freedom equal to t times the quantity of n minus 1. I'm going to be perfectly honest, I'm not going to be likely asking you to conduct a confidence interval or hypothesis test of a contrast. I'm at this stage in your learning development, I am more concerned that you're able to construct a contrast, meaning you're able to say, okay, this is something that is logical to be compared, and I need to create this logical comparison such that the coefficients add up to be 0. And then I'm going to be more concerned that you are able to assess those contrasts. And so what do I mean by that? So our contrast can be used to create an equivalent f-test. And so the sum of squares of a contrast is computed as our sum of squares contrast equals n times the summation of I equals 1 to t of ai times our row means quantity squared all over the summation of I equals 1 to t of ai squared. And as this is a if I should say the two-sided alternative is used, the test statistic from our previous slide can be taken as f equal to t squared equal to our sum of squares contrast over our MSW, which is compared to the f distribution with degrees of freedom equal to 1 comma t times the quantity of n minus 1. And so this leads us into our next discussion point, which is to talk about orthogonal contrast. In our previous part of this lecture, we talked about making one comparison. So we were comparing the black door in our mice example to the red and green door. We may be interested in comparing more than just that one specific comparison. And so, as we've established in previous slides, though, this idea of multiple testing does compromise the validity of our stated significance level. So what we do is we do something called orthogonal contrast, and this helps reduce the number of contrasts that we actually create. And so what are orthogonal contrasts? Well, first off, you need to establish that you have two contrasts. So two contrasts are if orthogonal if their dot product of their coefficients is 0. So to state a little more clearly, two contrasts, the summation of I equals 1 to t of ai equal to mu I, and the summation of I equals 1 to t of bi mu I are orthogonal if the summation of I equals 1 to t of ai bi equals 0. So to construct an example, let us say that we have our mice example and we were interested in testing the black door versus the red and green door. Following that, we are also interested in just comparing our new painted doors, so the red versus the green door. The first thing we should do is to assess that these are both contrast. And so I'm going to write, I'm going to make a little chart. So we have mu B, mu R, and mu G. And so for our first contrast, this would be 2, -1, and -1. And if things are done correctly, our sums should be 0. 2 minus 1 minus 1 equals 0. Excellent. Next, we have our second contrast. There is no mu B. Mu R is +1, and our mu G is -1. 1 plus -1 is 0. So we've just established that 1 and 2 are contrast. Now we need to check to see if they are mutually orthogonal contrast, which means we simply have to multiply our two contrasts together by their coefficients and add to see if we can get these values to equal 0. So simple, 2 times 0 is 0. -1 times +1, -1, -1 times -1 is +1. Add it together and we get 0. So therefore, our two contrasts are mutually orthogonal. And so what this does is it does allow us to conduct an F-test and save us the price of performing an extra test separately, which we'll be able to see here in a moment. And so what are some properties of our orthogonal contrast? So sets of orthogonal contrast do have some useful properties when the data are balanced, meaning all ni is equal to n. And for t factor levels, it is possible to construct t minus 1 mutually orthogonal contrast, meaning that each pair of contrasts are orthogonal. In our mice example, we had 3 populations, red door, black door, green door, and so we were able to construct 3 minus 1, orthogonal contrast. And so, nice, lovely fun fact for us that helps us out. So the sum of squares for the set of t minus 1 mutually orthogonal contrast will sum to the between factor of our sum of squares. And to give you an illustration of this, so if I were to test our two contrasts for our mice, and so I use JUMP when providing output for you guys in this course. And so this is what the JUMP output looks like when we are testing contrast. And so this is our first contrast where we compared the black door to the green door. And then our second contrast where we compared our green and red door. And what it does is it provides us with our mean estimate, our standard error, a t-ratio, and a p-value. And so what this allows us to assess is looking at our p-values, we are able to assess if there is a significant difference in our contrast. So for our first contrast, we were comparing black versus red and green, and we had a p-value of 0.0014. So that tells us that we could reject our null hypothesis and we could conclude that there is a significant difference between the times for the black door versus the red and green door. At this stage, we don't know which is better, but we do know there is a difference. And then taking a look at our second contrast, where we looked at the green door versus the red door, we can see that we had a p-value of 0.0004, and this would also tell us that we could reject our null hypothesis. So that tells us that there is also a significant difference between the times of mice going through a green door versus going through a red door. And if we were interested in taking a look at this as partitioned through our ANOVA table, it would look like so. But before we really look into this, I wanted to go back to the previous slide. This test detail also gives us our sum of squares. These two sum of squares added together equals our sum of squares between. That was what the note on the previous slide established. And so what it allows us to do is we can actually begin by testing our contrast as an alternative. And so we can notice our degrees of freedom gets partitioned between our two orthogonal contrasts. So each of these has 1 degrees of freedom. Again, our sum of squares will add up to our sum of squares between. We divide to get our mean squared error, or excuse me, our mean squared between, and then we can divide and get our F ratio. So taking a look at this, this is another way we could have assessed the contrast if we were not given the information on the previous slide. Let me take a moment. Let me erase what I just did. Okay. And so we could have used these overall F ratio to test whether there was a significant difference, at least somewhere in one of our colors. And then we could have looked more specifically using this F table, or excuse me, ANOVA table. And so taking a little bit further look at our orthogonal contrast. And so although we are using pre-planned contrast, obviously we are still testing multiple hypothesis tests based on one set of data. And we know the issue with this is that it does mess with the overall significance level. However, when we test K contrast, each at our significant level alpha, the probability that all K tests would fail to reject their true null hypothesis is 1 minus alpha to the K. And so if we're in the situation like in the mouse example where we're testing only 2 contrast, that means our true confidence level ends up being 0.9025, and so that's a little over 90%, and that's honestly not bad. Throughout this course, we've done things without having to have multiple tests, we've tested things at the 90% level. And so that's what I kind of say about being able to use contrasts that help us protect our confidence level a little bit. So we've really, for the price of 3 tests, we were able to still have a confidence level at 90% because we had our overall F test and then we were able to test our 2 contrast. And so that's pretty good. There are further procedures we can use to protect our contrast level further, or excuse me, our contrast level, our significance level further. And that's something we'll talk about more when we do post hoc comparisons. Because again, orthogonal contrast are something we do when we are doing a pre-planned comparison. So it's when we're designing our experiment and we're thinking ahead saying, well, I want to see what's going to be the difference. In the case of our mouse example, we knew that already that most doors are painted black for mice mazes, and we were testing the effect of changing the door color on the mice time. So we were able to know ahead of time what we were going to be interested in assessing. But sometimes that's not always the case, and we have to do something called post hoc comparisons. But before we do that, I do want to talk a little more about our objective 2 as far as what I would expect for you guys to understand. Because I do know this section can be a bit hard. And so really, again, I kind of mentioned already, but I want to emphasize what I would expect for you to know for your final that is quickly approaching. I would expect you to know how to construct a contrast. And if I were to give you, say, an output like this or like this, you should be able to assess the contrast. Is the contrast significant or insignificant? Looking at this output particularly, it should be pretty easy to see. We have an insignificant, we have a significant p-value, so that means there is a significant difference between the black versus red and green, and also the green versus red. And I would be expecting you to be able to do that. I'm not going to make you do the test themselves, but I do want you to understand how they work and how to start the problem off and how to understand how to assess the results of the problem. Because ultimately in your real professional lives, that's going to be the thing you're going to have to do most. You're going to have to look at a experiment prior to completion and know what contrast or what things you're going to be specifically looking for in the results. And once you have the results in your hand, how do you assess the final calculations or the test? The calculations part is something that really just comes in with using statistical software, and that's easy enough to learn. Okay, so this does bring us to our third objective, which is to talk about the post hoc comparisons. And so, as I've said before, some experimental situations do not lend themselves to pre-planned comparisons. For example, we might have a conjectured relationship between treatments that is not known prior to the experiment. And this shouldn't really be too much of a surprise for some people. Basically, you've got to start somewhere. So the solution to this problem is to use post hoc comparisons that specify hypotheses based on the observed differences among our factor level means. Something to be aware of, examining data before stating the hypothesis of interest is called data snooping, and it can lead to distortions of our stated significance level of our test. And so that is something to be careful of. But as I said, ideally we complete post hoc comparisons so that we can get an idea for pre-planned comparisons in future experiments. So as I said before, you kind of have to start somewhere. And so when we don't know what to look for ahead of time, we just do post hoc comparisons to conduct an experiment, see what we get, and then move from there. So there are various and complicated procedures that have been constructed to avoid error rate distortions for our post hoc comparisons. And what I mean by error rate distortions, I mean that what happens when we conduct multiple comparisons, and each comparison we make lowers our significance level. Some of them are easy enough where it just rises the original confidence level. So as I've said many times before, that standard confidence level is 95%. And if we do 2 tests, that brings us down to 90%. Well, if we started at each individual test being at a 99% level or a 99.5% level, then we can perform more individual tests or so that the overall significance level isn't impaired too much. The method we'll be most interested is looking at the Fisher's protected method. And what is nice about using a protected method is this method does not test or estimate any contrast or comparisons when the overall F-test of our all equal means has an insignificant result. And so if you think back to that ANOVA process I talked to in both last lecture and at the very beginning of this one, where I said step 1, assess your assumptions. Step 2, construct your model. Step 3, perform the overall F-test. If that overall F-test is significant, we finish. Because if at that stage we cannot conclude that there is a significant difference between the means as a whole, we're not going to go and quote waste our time to then look further into that data to try to find specific comparisons within the means and within each factor level. Because while there may be some slight difference, it wasn't powerful enough to affect the overall test. And so using the protected method, we end the experiment at that, or end the experiment analysis at that point. If we do have a significant overall F-test, we then will proceed to performing post hoc comparisons, and we'll be using the Fisher's LSD test. And this takes the square root of the residual mean square from the ANOVA table and considers that to be a pooled standard deviation. And then taking into account the sample sizes of our 2 groups or multiple groups being compared, the test computes a standard error of the difference between those means, and then it computes a t-ratio by dividing the difference between the means by the standard error of that difference. And then to compute a p-value and a confidence interval, the Fisher's LSD test does not account for the multiple comparisons. What it does is it basically does what I said at the very beginning was a bad idea, is it just computes a whole bunch of individual t-tests. And the only difference is that rather than compute the pooled standard deviation from only 2 groups being compared, it creates a pooled standard deviation from all of the groups. And so if all groups are sampled from populations with the same standard deviation, using all that data to compute a pooled standard deviation is actually going to give us a more accurate value of standard deviation that's going to be closer to that true population mean, at least theoretically. And so using our mice example, this would be an example of our results where we have a whole bunch of 95% confidence intervals for our black, green, and red door. Obviously black to black, green to green, and red to red, we have 0. And when it is in red, we have significant difference, and in black is when we have insignificant difference. And so we can see when we are comparing the black door to the red door, we have a confidence interval that includes 0, which means that it is insignificant. We, however, can see that there's a significant difference when we compare the green door to the black door and the green door to the red door. And so what that tells us is it tells us that green has a significantly different result than the red and black door. And this table here at the bottom is a pretty common chart that we do see in statistics when we are computing these kind of contrast, and they just show us where our significant and insignificant differences lie. So when we have items that are on the same level, meaning they're insignificantly different, they'll label them the same, such in this case, they're both red and black are labeled B, and our green level or our green door is significantly different and it's labeled A, so it's labeled differently than the other two doors. And so how could we interpret this as a problem? Well, we would say, using our Fisher's LSD protected method, we can determine that there is a significant difference between the time it takes to complete a mice using a green door as opposed to a red and black door. And so, as I said before, there are many methods to doing a post hoc comparison. There is Tukey's method, Duncan's multiple range test, Sheffy's test, and Bonferroni method. The two in the middle are not commonly used. In my very first graduate class, my professor talked about all these methods, and he flat out said the only time he used the two in the middle were when he was learning about it when in his PhD classes and talking about it now in our course. Otherwise, he never used it, and I'll be honest, I've never used it. Tukey's I've used, Bonferroni's I've used, but the two in the middle I haven't. According to him, and I don't know any different, my previous professor, he said what happens a lot is that statisticians trying to get their PhDs in statistics come up with slight variations of various other post hoc comparison methods that might slightly improve that overall confidence level. And so it's just kind of another thing added to the list. I don't know how true that is, but it does kind of make sense to me that people would try to keep inventing methods that are slightly better, but probably not significantly better than our original previously known methods. Okay, so what would I expect from you guys as far as the post hoc comparisons? I would expect for you to understand when we perform post hoc comparisons as opposed to pre-planned comparisons, particularly when we're doing our protected situation. So if the overall F-test is insignificant, then no, we're not going to move forward with any post hoc comparisons. Also, if I give you a result table like here in the mice example, I would expect you to know how to interpret this table. But that really is as far as I'm going to be expecting you in this course at this level. Stat 512 has a major focus on ANOVA, linear regression, multilinear regression, which are the last three topics of this course, or last 3 weeks of this course. So I'm not going to go into huge detail because I know a great many of you are taking that course, and I certainly wouldn't want you having to relearn material again and again. So this part of the course is kind of a give you an introduction so you have an idea, but there's still a lot for you to learn next semester. And so this brings us to our fourth objective, which is to talk about the random effects model. And so what is the random effect model? Well, during our previous lecture, we described this scenario where we were interested in the mean amount of debt for graduating seniors at WVU, OSU, and PSU, and 50 graduating seniors from each school were sampled. And so in our last lecture, we were really only interested in those 3 schools. And so we used a fixed effect model. If we were interested in the entire population of state universities in the US, that would be a case where we would consider our 3 schools that we sampled as a random sample of size 3 that would represent our entire population. And so for this, we would use a random effect model, and its corresponding methods used in chapter 6.6 in our textbook. And so under the random effects model, inferences on effects of individual factor levels aren't as meaningful because the factor levels in a particular set of data are a randomly chosen set. So instead, we focus on determining the magnitude of variation among the population effector levels. And so using our college debt example, if we were setting up our random effect model, it would be Yij equals mu plus tau I plus epsilon ij for I equal 1 to t and j equal 1 to ni, where Yij is our observation j, effector level I, mu is the overall mean. So far all the same as you saw for the fixed effect model. Where we are going to see some difference is here. So tau I is the random treatment effects of factor level I, which are a random sample from a normal distribution with mean mu and variance sigma tau squared, and our epsilon ij is the observation errors for the jth subject from factor level I, and our random sample from a normal distribution with mean 0 and variance sigma. And so under this random effects model, the hypothesis test of interest is that the null hypothesis is sigma tau squared equals 0 versus our alternative where sigma tau squared is greater than 0. And if that null hypothesis can be rejected, the next step is to estimate the variance components of sigma and sigma tau squared. This is not something we covered in this course. The only thing I truly would expect you to understand for fixed effects models is being able to write out the model and to be able to tell the difference between a scenario that is fixed effects versus random effects. So fixed effects, we are interested in using our college example, we were just interested in those 3 schools only. Random effects, those 3 schools were the sample of the entire population of state schools, and that was our population of interest. And so this brings us to our final objective, which is to complete a practice problem start to finish for our ANOVA process. And so let us look at a scenario, and this did come, the data set came from the book, but I did manipulate it a little bit. So assume the data represents gas mileage of automobiles resulting from different gasoline additives, and assume that each observation was randomly selected. So the second part of the scenario to know, as we saw, we had 5 treatments. Treatment 1 included additive A and was made by manufacturer 1. Gasoline 2 had no additive at all, and we were given no information about its manufacturer. 3, we had additive type B made by manufacturer 1. 4, additive type A made by manufacturer 2. And 5, we had additive type B made by manufacturer 2. And so the first thing we would do is to assess our assumptions. So I've given you these information looking at these tables and chart. And so we need to assess, do we have independence of our observations? Well, in the original problem, we were told that each observation was randomly selected, so that implies we have independence. Second, constant variance. If we flip back, we can see that we have the Levene's test, and ideally we want our p-value to be large. This p-value is 0.1422. That is greater than our assumed alpha value of 0.05. So therefore, we would fail to reject. And so therefore, yes, we have constant variance, or rather, we cannot prove we have different variances. And for non-normality, this should be unimodal and symmetric. Again, in this scenario, we were dealing with a sample size larger or less than 30, so we kind of have to do an approximate, and it does appear to be, if we had a larger sample size, I would say that it probably would look more normal. So I'm going to say it's normal enough and go ahead and say, yes, that holds. So because we have now assessed our assumptions, we've found them okay, it's okay to move on and construct our ANOVA model. And this would be our fixed effects ANOVA model. And so this would be Yij is equal to mu plus tau I plus epsilon ij for I equal to 1, 2, 3, 4, 5. And this is our treatment number. And j equal to 1, 2, 3, 4, 5. And that's the individual observation per treatment. And in this case, Yij would be the gas mileage for the ith car from treatment, or excuse me, the jth car from treatment I. Mu is our overall gas mileage. Tau I is the treatment effect of the ith treatment. So, mu I minus mu. And then epsilon ij is our observation error. From the jth car from the ith treatment, where our errors are independent and normally distributed, following the normal distribution with mean mu and sigma squared for our variance. So excellent. So we've now constructed an overall ANOVA model. And now we can ask, do our sample results provide evidence that one of these gas additives and or manufacturers are superior? And so in order to test that, we would start by constructing our null and alternative hypothesis. So our null hypothesis would assume that each of these treatments have the same average gas mileage. Our alternative hypothesis would say at least 1 mu I does not equal the others. And so as we are not using a statistical software in this course, I will either provide you with the ANOVA table that you would need for this, or I will, as I did here, give you a partially filled in ANOVA table and you need to fill in the rest. And so we can recall that for our sum of squares between, it is equal to our total sum of squares minus the sum of squares within to give us our sum of squares between. So this would be 155.628. Now we need to talk about our degrees of freedom. I personally prefer to find my degrees of freedom for the total and the degrees of freedom from between and then subtract to get within. Why? Because I can easily find the degrees of freedom total. It is our sample size minus 1. We had 5 additives, or rather 5 treatments, and each of those treatments had 5 observations. 5 times 5 is 25. So my sample size was 25. I can easily subtract 1 to get my degrees of freedom total of 24. In similar fashion, I know that my degrees of freedom for between are my number of populations minus 1. I had 5 treatments minus 1 equals 4. So I can subtract 24 minus 4 to get degrees of freedom within to be 20. From here, I just need to do some division. And this would be a mean squared between of 38.907, and mean squared within will be 0.7266, and this would give us an F ratio or F statistic of 53.5467. Excellent. So now that I have my F ratio, I may recall that we will reject F if it is greater than F alpha and our degrees of freedom 4, 20. So at this point, I can open up our F table. So I'm going to exit out of here, pull open an F table. And since there was no stated confidence level, we then assume it's 0.05, and we are looking for 420. 420 would be 2.87. And we can clearly see that 53.5467 is greater than 2.87. So therefore, we can very safely reject our null hypothesis. And so therefore, we can conclude at the 5% significance level, there is some difference existing between the gas mileage and additive used or treatment used. Lovely. Okay, so looking back to our data, so we have determined that we've got our 5 treatments and that there exists some difference within our treatment. Just looking at the data as it stands, I can clearly see that treatment 2 has lower values than the rest. And it kind of looks like treatment 3 and 5 have a little bit higher than 1 and 4. Can I prove that significantly? That's the question. And also, we have this to contend with. We know that each treatment had different additive types and had different manufacturers. And of course, treatment 2 had no additive. So this would give us an idea of some contrast we could make. So one of the contrasts we might be interested in would be to compare our scenario of no additive versus having an additive. Also, there were different types of additives, so I would be interested in exploring type A versus type B. And we also had different manufacturers, and so I would be interested in exploring manufacturer 1 versus manufacturer 2. And so to set up our contrast, no additive versus additive. The no additive, that was mu2, and we would want to compare that to mu1, mu3, mu4, and mu5. And to make that a contrast, we've got we got 1, 2, 3, 4. So 4 mu2 minus mu1 minus mu3 minus mu4 minus mu5. Type A versus type B. Type A, we had mu1 and mu4. And for type B, we had mu3 and mu5. And then for manufacturers, for manufacturer 1, that was mu1 and mu3. And for manufacturer 2, that was mu4 and mu5. And so now that we've constructed our contrast, we should make sure that they are orthogonal. So let's do a test of this. And what I'm going to do is I'm going to erase this part of it to give us a little more space for me to write and to make my little chart. So to start off, for the top of my chart, I'm going to write mu1, mu2, mu3, mu4, and mu5. And our last column is our sum. And so to start, I'm going to write out our coefficients for our first contrast. So this would be 4 to lots of negative 1s. Second one, 1, 1 for mu1 and mu4, negative 1 for negative 3, or mu3 and mu5, and a 0 for mu2. And then for the last one, we would have 1, 0, 1, negative 1, negative 1. So to start off, let's assess, make sure these are all contrast. Negative 1 plus 4 plus negative 1 plus negative 1 plus negative 1 is 0. That checks out. 1 plus 0 plus negative 1 plus 1 plus negative 1 is 0. That checks out. 1 plus 0 plus 1 plus negative 1 plus negative 1 is also 0. So we have created 3 contrast. Now we need to make sure they are mutually orthogonal. And that would mean by finding their dot product. Now what a lot of people do that is a mistake is they want to just multiply our 3 contrasts together. That is a mistake. Remember, the rule says it is the dot product of AI times BI must equal 0. So what we're honestly going to have to do is multiply contrast 1 times contrast 2, contrast 1 times contrast 3, and contrast 2 times contrast 3. And so we'll start by doing contrast 1 times contrast 2. Negative 1, 0, 1, negative 1, 1. And we can add that up, and that will equal 0. Looking good. Let's do 1 times 3. This would be -1, 0, -1, +1, +1. Again, that equals 0, so that checks out. And then finally, 2 times 3. This would be 1, 0, -1, -1, +1. And that also equals 0. And so therefore, we do indeed have mutually orthogonal contrast. Excellent. And so, which can come as no surprise to you guys, as we've now constructed our 3 orthogonal contrast, we should assess them and see where our information lies. And so let's start by assessing our first contrast, which was 4 mu2 minus mu1 plus mu3 plus mu4 plus mu5 equals 0 to the alternative of 4 mu2 minus mu1 plus mu3 plus mu4 plus mu5. And we were just trying to see if there was a difference that existed. And so by examining our results, we can see that we have a t-value of -11.97 and a p-value that is certainly less than 0.0001. So therefore, it is indeed safe to reject our null hypothesis, and we may conclude that there is a difference between an additive and the gasolines that have additives. And because I'm going to try to put these all on this slide, I am going to have to abbreviate a little bit, so I do apologize. All right, so our second one of interest, we had a contrast of our additive A versus additive B. And so this would have been mu1 plus mu4 minus mu3 plus mu5 equals 0 to the alternative of mu1 plus mu4 minus the quantity of mu3 plus mu5, which does not equal 0. And we are given a t-value of -7.975 and a p-value that would also be less than 0.0001. So once again, we can reject our null hypothesis, and we conclude that there is a significant difference between additive type A and additive type B. And so the last thing we are going to assess is the 2 different manufacturers. And so this would be a null hypothesis of mu1 plus mu3 minus mu4 plus mu5 equals 0 to the alternative hypothesis mu1 plus mu3 minus the quantity of mu4 plus mu5 does not equal 0. We were given a t ratio of, excuse me, there we go, of -2.256 and a p-value of 0.0354. And so at the alpha alpha equals 5% level, there is a significant difference. Notice if we had gone to the 99% confidence level or 0.01 significance level, this would have been insignificantly different. But that's why we make our significance level prior to the problem. So therefore, we might reject our null hypothesis, and we will conclude that there is significant difference between our manufacturer 1 and manufacturer 2. Excellent. I know this was a lot of work, but we did get some nice results. And last but not least, let us take and think a moment about the situation where we had no pre-planned comparisons made. And so what should we do next? Well, as we had a significant overall F-test, that means we could move on and do, say, the Fisher's LSD test, where we have a whole bunch of t-tests. And using our results, we would say that given the results of the JMP report that I have provided with you, we can see that there is insignificant difference between treatment 5 and treatment 3. There is difference at level 4, 1, and 2. And as we were thinking of gas mileage, we ideally want higher gas mileage, meaning we want to go further per gallon. And so we would want the highest mean. And so therefore, given the results of the JMP report, there is insignificant difference between treatment 5 and 3, but these treatments are significantly better than treatments 1, 2, and 4. And if we were curious, so I would say, therefore, if we were a shareholder in the company, I would want to be using the gasoline that was for 5 and 3. And because we have the time and we're curious, what was 5 and 3? 5 and 3 were additive type B, and they were moved from both manufacturers. So that would tell me that it would be better to use the additive type B in the gasoline for improving gas mileage. Excellent. All right, so that does bring us to the end of this lecture. What should you be doing at this point? You should be reading chapter 6, sections 4 through 6. Note that this is not the end of the chapter, but it is the end of the material we're covering in this chapter. and you should be completing the knowledge check that is associated with this lecture. If you have any questions, as always, please send me an email. Have a good week. Have a good night.